Thanks for joining this webinar. Today, as you already see and know, we are going to focus and talk only about SQL capabilities of Ignite. And I'm pleased to be joined by Igor today because this session we decided to kind of achieve two goals with it. First of all, this session will be useful if you are beginning and starting developing your very first applications with Ignite, as well as with the help of Igor. If you already use Ignite actively, you will understand some like deep internal mechanics of the Ignite SQL engine, memory usage, etc. That's why our topics for today look as follows. First of all, we'll start with the basics. I'll explain you what are the connectivity options, how to configure your cluster, whether you can use DML, DDL, or any other approaches available in the platform. After that, we need to explore and understand the affinity collocation concept. I do believe that many of you are already familiar with that, but in this topic, we will see how that affinity collocation concept is related to SQL. For instance, usually if your data is collocated, then you can benefit from running high-performance distributed joins. Those two first items will be presented by me, and after that, I will hand over the mic to Igor, who will go deep in the woods, explicating on the internals of our multi-tier memory architecture, especially how our SQL engine is integrated with our memory management system, how our SQL engine can read data not only from memory, but also from disk. The same section will be finished with the introduction of a brand new feature, memory quotas. With those capabilities, you can tell Ignite precisely how much of a given memory space can be consumed by your SQL queries. So that's an excellent thing to have in your toolbox, and I will let Igor to elaborate on that. And finally, Igor represents the group of Apache Ignite contributors and committers who are developing right now a brand new Ignite SQL engine that is powered by Apache Calcite. Igor will tell you the motivation, why the community decided to go for with this new development rather than, just to keep improving what we have right now. And also, you will see a workable demo of this prototype that executes queries, SQL queries, that are not possible to execute with the current SQL engine of the project. And speaking of the demos and samples, throughout this whole section, both Igor and I will be kind of switching from the slides and showing you some of the nice demos that you can use as templates for your applications. But having said that, let's move on with our basics. What's Apache Ignite SQL? Generally speaking and shortly, that's just the same standard familiar SQL that is designed to work at scale across a cluster of machines. Ignite supports a standard ANSI 99 specification. We support data modification language statements as well as data definition language statements, which include selects, updates, create, etc., etc. You can join your data stored in your distributed Ignite cluster. You can do group operations. You can sort the data. Everything that you are getting from classical relational databases. At the same time, when it comes to the runtime changes of your data structure, if you need to alter your table by adding new columns or removing some of the columns from the SQL metadata, or you want to create a new index or drop an existing index, it's all possible to do with Ignite. So from the specification standpoint, you're getting a pretty sophisticated SQL engine that supports a broad range of capabilities. And finally, what distinguishes Ignite SQL engine from the SQL capabilities of other in-memory products is that as an in-memory computing platform, we by definition can read data from memory. But also, if you enable Ignite native persistence, Ignite can function as your full-fledged database, meaning that if Ignite SQL engine cannot find any piece of data, bit of data in memory, it will serve it from disk automatically. And we don't need to do anything with our application code. That all happens transparently. Igor will tell you more these disk-based capabilities related to the SQL. Next, guys, what are the connectivity options? I would define three primary approaches. First of all, you can use thick clients Also, think about thick lines as of our software development kits available for Java, C# or C++ developers. As part of those software developers kits, certainly we have Java APIs, and you can just take, let's say, standard Ignite call library that can start a thick line of Ignite, embed into your Java application, and that the same library will list SQL-related methods that you can execute and run from your application. An alternate approach is to benefit from the JDBC or ODBC drivers, especially that would be useful if you want to connect to the cluster using any SQL tool like Tableau or anything else. If there is plenty of such tools. And finally, if you are not programming in Java, .NET, like C# or C++, but your primary language is Python, Node.js, PHP, or any other, then consider our thin client APIs. Thin clients are more lightweight representations of our client connectivity capabilities to an Ignite cluster, and also the thin client APIs support SQL methods. So you can connect from Python to a cluster, and you can issue SQL queries. Next, what's about configuration options? And with the following slides, I will be focusing only on Java. But generally speaking, if you are a .NET developer, C++ developer, etc., then you just can go after the session to our official documentation and see how to configure SQL with those languages. So speaking of Java, the very first configuration option is to define your SQL metadata programmatically using annotations. So as it's shown on this slide, let's assume that you created a city project class. And if you want any of the fields of this class to be visible by Ignite SQL engine, then you need to annotate those fields using query SQL field label. At the same time, if any of these fields need to be indexed, then just pass in an additional parameter index equal to true. And once you annotate all your POJs this way, whenever you are creating a cache configuration in Ignite, then you need to pass in these annotated POJ classes into the setIndexTypes method. Speaking of caches and tables, because throughout the conversations, usually I will be referring to tables. But in Ignite, you know, like when you're dealing with caches, usually you are using key value APIs, so like cache abstractions. But generally speaking, there is no any difference between caches and tables in Ignite. And we use those terms depending on the APIs you are working with right now. And the reason why we have cache configuration on this slide is only because as part of that configuration, you have that setIndexTypes method. Another, and speaking of the usage scenario, when I personally see this method to be used, generally those of us who who enjoy the Spring style development, like when you know that the Spring ecosystem and frameworks encourage us Java developers to annotate like our controllers, services, repositories, etc. And you can continue doing this with your Ignite powered applications. If you want to keep annotating Ignite POJs, annotate. But anyway, so like if you want to do any runtime changes with your SQL metadata, things like you want to add a new column or you want to add a new index or drop an existing one, you always can run our DDL statements like create index or alter table. It's all available, even if you can do the initial configuration this way. The second configuration option is when you want to configure the same SQL metadata using Spring XML, using query entities objects. Internally, query entities are even used when you annotate your objects, but that happens behind the scenes for you. When you pass in your annotated, let's say, objects, POJs, to the setIndex class, then internally Ignite will produce query entities. But also those query entities, those are public APIs, and you can use them in the Spring XML configuration. And this method, I find it being used for use cases when Ignite is deployed as a cache, as a write-through cache, or also it's named as a data grid on top of your existing relational database. The reason is that if you deploy Ignite in such configuration, you can use GridGain Web Console that can connect to your relational database and turn the database schema into like cache configuration of Ignite with query entities. like there is some automation in place. That's why if Ignite is used as a cache, with this configuration, usually you would use GridGain Web Console to generate the configuration like the one you see to the left on the slide, and then you would be just running your Ignite cluster, and that cluster will be writing through all the changes to your underlying database. And the final approach, for sure, as soon as we support ANSI 99 SQL, nobody prevents us from using an old good style like pure SQL, creation of the tables, etc. And this approach, in my experience, people switch to it if they're writing SQL-driven applications, when most of the operations are executed using SQL commands. And especially here, as we are talking about greenfield applications that are developed with Ignite, and especially if those greenfield applications need to persist changes in Ignite's native persistence. All right. That was the very first speed dating with our Ignite basic SQL capabilities. I hope that that section is precisely for the Ignite beginners, so that you can understand what are the primary capabilities of Ignite. I did not want to go deep in the woods, so the rest of the information you can research on the official documentation. But as of now, let me show you like a simple demo. I want to start a 2 nodes cluster. I want to connect to that cluster using our Ignite JDBC driver and create a database in Ignite using SQL, using DDL statements, right? So that's the context about the demo. I'm switching to my terminal window. So first of all, I have downloaded Ignite of version 2.80. And right now I'm starting my first cluster node. Let's give it some time. Luckily, I have upgraded to a new laptop, and right now the boot time is tremendously minimal. All right, so the first node is running. Let me start another one. I want to have at least some distributed solution, even though the cluster is running on my machine. All right, I have 2 cluster nodes. And the next step, what I'm going to do is I want to connect to this cluster using our JDBC driver. And this JDBC driver will be used by the SQL line tool. That tool, the script of this tool and jar files of this tool are shipped with Ignite binary releases. And that's how I will be connecting to my cluster. I just need to pass in this JDBC URL. So I'm connected to my cluster, and next step, I want to preload a database. I have one here, so that's the script that is located in the demos. By the way, this demo project will be, you will get it, so it's already publicly available and released, and you will get a reference to it on our last slide of this presentation. But anyway, so let me load this script, and I will show you what's inside. So the database is preloaded. It's tiny, it's small, probably just takes only a few megabytes of our Ignite cluster. But anyway, so that's what goes inside of this script, like country table, city table. We are defining primary keys, and also we are associating this table with specific caches. I just usually do this because sometimes I want, in addition to SQL APIs, I use key value APIs, or I can execute compute APIs. And for those APIs, you need to pass in the name of your cache that is associated with the table. So that's why I do this, but that's optional. All right, so the next step, let me show you that the cluster is up and running and that we can at least execute a primitive SQL query. To do that, I will be connecting to the cluster using GridGain Web Console. I did my homework and downloaded a special web agent that will be interconnecting my local cluster with the instance of GridGain Web Console deployed, hosted by GridGain. So let me refresh the screen. So fingers crossed, hopefully there are no any issues. And right now this hosted version of the tool connected to my cluster. Yep, lucky I. So here is my 2 nodes. And next, I prepared before this talk, I prepared this simple notebook with Ignite. And what I want to do next, I want to run this simple query. No any joins, no any only order and group by. So generally, what we are doing here, I want to get most populated countries, and I'm querying only one of the tables I've created with the script. All right, Web Console as always. Sometimes you can show me an exception, but if I re-execute this, I will get the result. China, India, United States are ranked at the top 3 most populated countries. All right, so that was the first demo. Just remember it. Start the cluster. You can connect with JDBC. You can create with DDL, etc. You can just start running your queries. So next, what are we gonna do next? We need to switch to the next section of our today presentation and to talk a little bit about affinity collocation and how the affinity collocation concept and technique is related to the distributed joins. But first of all, let me show you how. Let me tell you a little bit about internals of Ignite SQL engine. So here, as we can see, 3 nodes cluster. And it's obvious that as long as every node is capable of processing our SQL queries, then there is a kind of special code running on every cluster node. But when we are talking about our Ignite SQL engine embeds H2 database engine. We use H2 to produce execution plans. So we're using the planner and optimizer of the database to produce like the physical queries that will be executed by those 3 cluster nodes. However, it's also worth mentioning that it doesn't mean that we use H2 to store our data in indexes. Quite opposite. All the data and all the indexes are stored in Ignite multi-tier storage. So we handle that, we manage the memory, and we decide how to put and how to allocate and how to store all your data and all your indexes. And again, H2 is used only, to produce a proper result, like proper execution plans when you decide to run any query with Ignite. And there are 2 query execution phases with Ignite, the map phase and the reduce phase. Let's imagine that our application that is named here like thick client, probably not the best name, but okay, that's your application, Java application or .NET application that wants to run this query that returns the average populations of all the cities of all the countries. So generally what happens next, your client application will just send this query through Ignite SQL APIs, and then internally Ignite SQL engine will execute the map phase. This query will be transformed to the one you see on the slide. And then this query will be executed locally on those both cluster nodes. After those nodes complete the execution of that query, they will respond to your client, returning their part of the result set. And the client will reduce the result set, preparing a final one that will be returned back to your application later. And when it comes to the data distribution, so let's say that we created 2 tables. We have country table and we have city table in Ignite. And generally speaking, by default, all the data will be distributed randomly. So at Ignite's best effort, Ignite doesn't know whether there is any relation. But we know that there is one obvious relation between country and city tables, is that all the cities are located in one of the countries. That's why we already can see that Toronto and Calgary are stored on the same machine where we have the primary record of Canada. That is good. But also what might happen is that some other Canadian cities like Montreal or Ottawa can be located on a different node. And the same is true about the cities of France, as you can see on this slide. But generally speaking, why do we have here the warning sign? It might be okay for you to have this distribution, especially if you just run simple SQL queries, if you don't need to iterate all the cities of a specific country, or you're just using key value APIs. But if you want to run more advanced SQL queries, such as those with joins, then you can trigger data shuffling between your nodes. Let's assume that now our thick client wants to execute this query that joins data stored in country and city tables, and when this query will be mapped to those 2 cluster nodes, those cluster nodes will start executing the query locally over the data set, but when they come to the join phase, they will start talking to each other and moving data from one node to another. With this tiny small database, it's not a big deal because you would be moving only 3 records, but imagine that if you're trying to join tables that need to join, let's say, thousands of records, like hundreds of records. And if you start moving those hundreds of thousands of records over the wire, if you enforce the data shuffling, you can lose benefits of your in-memory cluster because network is slow. And with data affinity collocation concept in mind, we would like to achieve this state of our cluster. We want all the related data to be stored on the same cluster machine. For instance, right now you can see that all the cities of Canada are located on the same cluster node, and the same is true about the cities of France. What we as application developers need to do, we just need to do only one small tiny thing. Whenever you will be defining the primary key of your city table, just specify the name of your affinity key, which is the country code in this case. And once you do this, it's obvious that when you ask Ignite to execute the query of this kind, when you want to insert a new record in the cluster, Ignite will take the value, it will use the value of your affinity key to calculate a partition number and then to calculate the target node. With this calculation, it might happen that the first node should store this record, but also to recapitulate here is that as long as all the nodes that have the same country code value, like all those nodes that have the same country code value, but automatically will be placed on the same cluster machine. And that happens, internally and automatically in Ignite. You just need to specify and set what's your affinity key. And right now, if you re-execute, rerun the same query, keeping in mind that the data is collocated, then the query is mapped, the query is executed locally, and there is no any data shuffling between the nodes. And that's ideal, because right now you can scale your cluster to hundreds or like dozens of nodes and thousands of nodes. You can store terabytes of data. And if most of the data is collocated, then you will be able still to benefit from your distributed in-memory cluster because there is no any data shuffling. All right, the final demo before I switch the stage to Igor. Let me run some of the queries with joins. So I'm going to use the same cluster, and here is I have another query prepared for you. So the one that returns top 3 populated cities in the following countries. So I'm joining data, etc., and filtering data, and so on and so forth. If I run this query again, my web console fails. Let me do this twice. Yeah, something wrong with the tool, but anyway. So that's the answer, but that's not the right answer. And here is I need to enable this checkout button, saying that when the next time you're going to send this query to Ignite, ask Ignite to run non-collocated joins. So basically, ask Ignite to shuffle data between the cluster nodes to produce a proper result set for me. And with this case, that's the right answer. Seoul, St. Paul, and Shanghai are the most populated cities among these countries. But we involve data shuffling to get this result set. So actually, those 2 cluster nodes running from my terminal window, we're shuffling records between each other. What can we do about that? Let me recreate the database, and I'm going to use another script that defines affinity key. I created this database, and let me show you the source code of that script. So here it's all the same database, the same data. The only difference is that when I was creating city table, I instructed Ignite that, look, Ignite, my affinity key is country code. That's why, please, when I will be sending any put requests or inserts into the cluster, Ignite will put all the records with the same country code on the same node. And right now, let me refresh the screen just in case. Right now, I don't need to have any data shuffling. All the data is collocated, so we're unchecking this button. And if I execute this query, you see this right answer, Seoul, St. Paul, and Shanghai. So right now, all the data collocated, we're getting the right result set, and no data shuffling is here. So generally speaking, so right now the performance was the same, right, between like non-collocated and collocated joins, because the database is small. But imagine that you're deploying terabytes of data, you're storing terabytes or gigabytes of data. The performance difference will be tremendous, like between non-collocated and collocated joins. So keep this in mind. Affinity collocations is one of the golden techniques in your Ignite toolbox, and use it whenever you can. All right. Having said that, let me turn over the mic to Igor, who will introduce you to the internals of our multi-tier storage, and we'll talk about memory quotas. So
Okay, so in this section, I'm going to tell you about multi-tier storage architecture and in-memory tier and Ignite native persistent tier in particular. Also, they will cover some typical issues you may face with running your SQL queries, and I'll show you how to solve them. So let's move on. Here I listed tiers. Our multi-tier storage architecture consists of. First of them is in-memory tier. It's used for high performance computing and in general in-memory caching scenarios. Second one is Ignite native persistence. So it brings crash recovery capabilities and allow your data to survive between cluster restarts. Also, it allows you to put as much data into your cluster as your disk is able to store. And the last one is external database or third-party persistent storage. It is useful then you want to speed up your classical relational database with Ignite. Also, it allows you to modify your data using Ignite APIs, and all the modifications will be replicated to classical relational database with write-through and write-behind capabilities. So here I tried to visualize in-memory tier internal structure. So here we have several memory segments. Each segment splits into pages of fixed size, and each page have its type and stores data of particular type, like index pages you see on the screen. Here index pages form B+3. It's data structure they use for our hash and sorted indexes. So you see root index pages refers to index pages on lower layer, and the pages on this layer refers to leaf pages at bottom, and all the pages refers to key value pairs or tuples on a data page, and all together they form our indexes and partitions. Then native persistent is enabled. Disk layer appears here. So at now each page in memory segment is a copy of the same page on a disk. All write and read operations happens in memory still. The only difference now is that a page is loaded from a disk on first access, and after modifications, all modifications flash back to the disk during checkpoint process. So they use page ID to navigate between pages. It's like a hard link that points to a position in a file. They use this pointer to load page and during checkpoint. Also using pages loaded pages map, they can turn page ID into a pointer in a memory segment and use it during read and write operations. All I said before was about disk and off-heap memory. Of course, Ignite is a Java middleware, and they widely use classical Java heap. So they use, while SQL query processing, we use it at parsing time, at planning time. Then they are scanning indexes and tables. They load records from off-heap memory into Java heap and uses them during computing. At computing phase. I mean filters, joins, expressions, etc. Here we need quite more heap than on previous phases. So let's describe why it's so. Here we have a simple query like the one Dennis already showed you, and this query might be represented as a relational operators tree. This tree shows how our system executes this particular query. Here we have our tables at the bottom of the tree and relational operators upon them. Here we have filter operators, join operators, projections, aggregations, and so on. So let's look at sorting operator. So you know when you want to sort something, you need all the set at place. So all these operators are written in Java, and they use Java structures, and they need to have all the data on heap. That means to sort your data, they need full data set in heap. Also, they need full set in heap to aggregate your data. Actually, they need it just to save aggregation group. So that does it mean? It means that running hundreds of such query, sooner or later, you will run out of heap memory and get out of memory exception. So this exception cause node crash, and I guess it isn't you wanted. But they have an option. The option is query memory quotas feature. So look at this simple example. Here we have two properties. First of them is SQL query memory quota. It limits how much memory any H query on a single node can take. And here SQL global memory quota. It limits how much memory all queries running on a single node can take. So then a query exceeds this limitation, an exception is thrown. So it's a recoverable exception, so you can handle it in your code, for example, rerunning failed query. So this way your cluster nodes will be alive and the system will have a progress. That's the goal. But you know, classical relational database doesn't have such limitations and such issues at all. They are storing everything on a disk, including operational datasets. Why don't they do the same? Let's flash on a disk sorting operator, operational data, and our aggregation group too. So actually they can. Look at this configuration example. Here we have another option, SQL offloading enabled. So this option changes a bit previous options behavior. So at now, then a query exceeds its limitation. No exception will be thrown, but the query will start flashing its operational sets on a disk. So of course it will slow down a query and will slow down a query significantly, but all the queries will finish successfully. That's the goal. So let me remind you, then you need quotas and offloading enabled. You need it, then you have sorting operators and in your queries, like order by instructions, when you have grouping operations in your queries, like distance or group by instructions, and then you have complex subqueries in your query set. So that's a demo time. Just a second. So I prepared a demo. They need for that two cluster nodes. And let's start on this simple configuration. Yeah. Let's look at the sources. So here we have a small memory region. It's just 10 megabytes. So enabled metrics, and also a template for our future tables. Here I just changed partitions count because we need some space for metadata, and 10 megabytes isn't enough for 1000 partitions. So I just a bit decreased their count. So let's check. Yes, our cluster is started, and now they need to load some data. Yeah, I will use SQL line for that. And first of all, they need to create our tables. Yeah. In my example, I use fielding log. It's a log of moving of baseball players for several years. And now they need to load our data. Yes, I will do it using copy command. You can check how to use it on Ignite website. let's try. Let's wait a bit, and we've got an exception. What does it mean? That means what 10 megabytes isn't enough for this amount of data, and they have Ignite out of memory exception and one node crashed. So let's restart our cluster with another configuration. I'll just shut down this node and start it with another simple configuration. Let's check what they have. It's almost the same configuration, but this additional parameter, persistent enabled. So they enabled persistent for default data region. So since at now the cluster have persistent enabled, they need to activate it using Ctrl+SH activate command. So that's fine. And let's try to load our data. Once again, they need to reconnect to the cluster because it's a new one. And they need to recreate our tables because it was an in-memory cluster and there are no tables at all right now. And let's load it. Let's load our data. So there are quite a lot of data. Yeah, 100,000 rows affected. So let's check. I'll use again Web Console tool. And let's run some simple query. Yeah, all the data is in place. So because they have persistent enabled, we can just restart our cluster. Let's check if it's work. If it works. Yeah. And let's start it again. So yeah, and now they just restarted our cluster, so they don't need to activate it. So it was auto activated. Then all previous nodes become online. And now, if they look at our metrics, they have default memory region of 70 megabytes and only 20 megabytes of available RAM in our segments. So now all the data is on disk, but they can easily select all of that. So this exception is expected because they restarted the cluster, so they need to reconnect it to create another session. So our data is loaded from a disk, as I said in my slides. So let's return to the presentation and to its second part. So here I'm going to uncover our plans to replace H2-based engine with a new one. I'll tell you why they decided to do that, and I'll show you how they solve such limitations in our new engine. So first question, why do we need it? As Dennis said in previous sections, each query processing splits into two phases, map phase and reduce phase. On map phase, the executes a set of map queries and aggregate them on a client during reduce phase. That means that each query splits into a set of map queries and one reduce query. But in this particular example, they have an aggregate in the query condition. So this query requires map reduce phase, and this condition requires another map reduce phase. So that means that they need two map reduce cycles to execute this particular query. Current H2 based engine can do that. Of course, you can split manually this query, rewrite this query into two runs and calculate aggregate first and use its result in the second query and get the right answer. But that means that they will force our possible users who want to replace their classical relational database with Ignite to rewrite all their queries. So I think it isn't what they want. To solve this limitation, they start works on a new engine a bit ago. And let's look at this slide. So here you see a typical execution flow, almost the same flow happen in any relational database on a market. So here we have user. He runs SQL query. The query parses the parser and validates against schema, and after that query AST is built, and this AST goes into optimizer. Optimizer optimizes it and builds a query plan. They execute this query plan and provide a user with result. So looks simple, I think, but almost all these components quite complex for implementation. So to be honest, they require months or even years of developing. But fortunately, there is a library, Apache Calcite library. Actually, it's a framework for query engines building. It has almost all components I showed you on this example, except a storage layer. So here we have JDBC client, JDBC serial, SQL parser and validator, and both query optimizers, heuristic and cost-based one, some pluggable rules, and so on. At this side, all that they need is just provide Apache Calcite and access to user data and get working SQL engine. So obviously it isn't true. There are several issues like lack of distributed query support, lack of indexes support. Also, they need some other subsystems. So first thing they need to implement is a splitter, and that splits our query into query fragments and make them distributed. Yeah. Runtime suitable for executing distributed queries. They need indexes support because Apache Calcite was aimed at first to run analytic queries without indexes at all. Also, they need DML and DDL support that they have in H2 engine at now. So, at now, let's look how currently they execute queries in the new engine. First thing they need to do is initial plan building. Here we have a text query that turns that is turned into a query AST, which becomes an initial query plan or relational operators tree, like the one I showed you before. And now they need to optimize this relational tree. At the slide, you see internal structure, cost-based optimizer internal structure. Here we have an estimator. It calculates how expensive to execute the query is. They use this cost in plan generator. Plan generator generates another relational tree, which is an equivalent to previous one, but has different costs. And they do the loop until they run out of planning time or they find the best plan ever. So we have a plan, but they need to split it. What they do here? They add a synthetic node. It's a query cursor or consumer node, and now they need to split it. The query, let's assume that persons and departments are collocated, so they need to reach collocation property, and they need to split the query and do some reshuffling. First day we can do that, just sending persons to their departments and do all the operations at department side and aggregate the result on a client. Or send departments to persons and do almost the same and aggregate the results on a client. Or send persons and departments to a client, do all the operations at the client side and get a result. Actually, our cost-based splitter checks all possible ways and chooses the cheapest one. So now they are able to execute our query. For that, they implemented reactive execution flow. You probably already seen such picture, for example, on sites about reactive Java streams. So this execution flow a bit similar to them, and this is the best choice in terms of resources utilization. So they use reactive execution flow for that. And let's check if the query from my previous slides is working and that they managed to achieve at this point. Second, I shut down our previous cluster. So they don't need the agent, this one. So third thing they should do is to build Ignite distribution from sources. Of course, I've done it before, but I left some instructions how you can do it by yourself. So let's start 3 nodes cluster with simple empty configuration. This one and this. Yes, 1, 2, 3 nodes. All nodes are online. And connect to the cluster using SQL line. So the thing they need to do is to create our tables. Fields. Yeah. this one. It's a simple script. Let's look at this. Only table with name, salary, ID, and 3 records. Let's execute the query. And suddenly our winner is Nikolai, which isn't true, you see. Let's reconnect to the cluster with another special secret parameter. And now we will use experimental query engine in our queries. And do and execute the same query. So first call is slow because our engine requires some warm-up, but the result is correct. Next executions are way faster. So you see our results at this point. So I'll take a voice back to Dennis now. Thanks for your attention.
Yeah, thanks, Igor, for this demos, and thanks for leading us deep in the woods, explaining how the memory architecture is designed and what are we doing, what the community is doing with the new SQL-based engine. If you don't mind, could you please show the last slide? I don't want to switch our screens once again. I will just do the summary and we'll explain the guys who are still on the line. Yep, what are the what they can do next. First of all, folks, as you can see, when we are designing and creating this session with Igor, first of all, yeah, we wanted to target only the beginners, those of you who are developing their first applications with Ignite. But then we kind of took a pause and kind of decided, no, let's kind of do both. We can briefly mention what are the basic capabilities of Ignite, show how to do the affinity collocation, etc. But then let's explain how the things work internally, because many of you are architects, many of you are I kind of letting Ignite to run some advanced workloads and applications, and that's why we wanted you to understand how Ignite is designed internally, how our memory management system looks like, how we store data and pages in memory and on disk, how you can what you should expect from the new SQL engine. That's why I think that all that knowledge and material will only benefit you. But having said that, like on this slide, first of all, we have a special documentation section about Ignite SQL capabilities. So there you can find all the details about the supported SQL specification, some other details related to the tuning, the memory quotas feature that was introduced by Igor. It's not available in Ignite, at least yet. Presently, that feature is available in GridGain Community Edition. That's a free version of GridGain that can be installed. You can install it and you don't need to pay for it a penny. So just check the documentation page and see how you can enable memory quotas for your deployment environments. Finally, all the demos that both Igor and I showed you today can be found on that GitHub project. And also, speaking of the Apache Calcite-based engine, today, like when we were explaining the motivation, we brought to the table only the case with subqueries. But certainly, there are many more reasons why we decided to set off this journey and to create the new SQL engine. And the subqueries is one of the reasons. But if you want to learn more, if you want to see what's the current progress, etc., if you are SQL database expert and also wants to join the development of this new engine, then just go to this wiki page and kind of learn more details. But having said that, thanks for coming. And if you have any questions, I don't see any questions in the section window yet, but we can, if you still have something in your mind, that's your chance to write the question down. Otherwise, folks, thanks for everything.
So,
Benkat, let me hand over the mic.
Perfect. Thanks, thanks, Dennis and Igor. I do see a few questions, actually, a couple of questions. I posted the
Strange.
links to everything, you know, on the slide in the chat window as well. So if you want to click around, you know, audience, feel free to click around. And then one quick thing, I also posted a link for our the next week's webinar, which is actually I mean, that's coming in 2 weeks, and that's a joint presentation with folks from Teradata, which will feature a customer case study. So, you know, if you want to check that out, that is something to look at as well. As I mentioned, I do see a few questions here. First question is, I think this came early, Dennis, in your section. Is there support for Hibernate and entity annotations in Apache Ignite?
So Apache Ignite integrates with Apache Ignite integrates with Spring Data, so those annotations, some of those annotations should be supported. But generally speaking, entities, I think that Hibernate is the same. We have integration with Hibernate, and I do believe that you can use those annotations. But this entity annotation is specific for the framework, such as Hibernate or Spring Data. It's not somehow used by Ignite. I mean that if you, let's say, have your Hibernate entities in your application, then you can use that, like you would use that entity annotation to kind of tell Hibernate or Spring Data that that's like special entity in my application. Please use dependency injections for them. But also you can keep using Ignite annotations, Ignite specific annotations, like those SQL fields queries to annotate the fields that will be visible to our SQL engine. And those, yes, and those that annotation, query SQL fields annotation, will be processed and will be and it is understandable by Ignite, to put it this way. Hope I answered your question.
Awesome, that's great. And then again, another question from Benoit was to avoid out of memory. This came in Igor's section. To avoid out of memory situation, can we define a TTL and LRU to flush the data and query the native or external database when the data is not available in memory?
So here is several options. We did not get into details with like some generic best practices on how to avoid out of memory issues, and rather focused on the memory quotas that are specific for SQL. But like what Igor demonstrated here when he was showing when it was not possible to load a database, sample database in Ignite cluster because we were running out of memory. In that, and if you remember, then he restarted the cluster with a new configuration that enabled Ignite native persistence. And with that native persistence, we were able to put all that, how many, like 650 megabytes of data in the cluster. So like first thing, like to answering your question, if you generally want to solve this problem when you're running out of memory capacity, you can use Ignite native persistence, because with the native persistence, all the data set will be kept on disk, and as much as possible will be cached in memory, depending on your memory resources. And as you remember, Igor showed you that when he killed that, stopped that cluster and restarted it back, no data was no data records were in memory, and then he just executed another query, and all the data was served from disk. So with persistence, with the native persistence, you are getting two excellent things. You will avoid any out of memory exceptions just because you're running out of RAM. And second of all, during restarts, you don't need to rehydrate your memory. Once your cluster is interconnected, Ignite will be able to serve all the data from disk, warming up memory space in background for you. That's one first option, right? The second option, as you said, yes, certainly you can set up different expiration policies, eviction policies, and then you, like, if any of the records is missing, you can bring it from another database, like Ignite can read it through, right? But in that case, remember that Ignite, if you use Ignite SQL, then Ignite SQL requires you to have all the data in memory if you're using a third-party persistence like relational database. So let's say that you designed Ignite with MySQL or Oracle, and so MySQL or Oracle persists your data. And then some of the records were evicted from memory because you didn't have enough space. But if you used the SQL queries, that means that you will start seeing incorrect result sets, because Ignite SQL cannot know that some of the records are missing in memory, and it will not generate any specific queries to retrieve the data from Oracle or MySQL. that feature, like automatic, like read through from Oracle or MySQL to Ignite to the Ignite cluster, works only for simple key value lookups, like cache get or like cache get lookups. When we know, like when we're looking for a specific record, and we know its primary key, and if that record is not in memory, then we will take it from Oracle or MySQL from disk. So generally speaking, if you're using key value lookups only, and you don't use any SQL queries, then yes, you can use this configuration of Ignite, an external database, and let's say eviction policies. Otherwise, just if you wanna solve this problem generically, if you wanna persist changes, if you wanna load data from disk, if it's not available in memory with your SQL queries, then use Ignite native persistence.
Awesome. I think we're out of time. I do see a few other questions. What we'll do is we'll reply to those one-on-one separately after the webinar. But I think we should probably end the Q&A section right now. And as I mentioned, we have recorded today's webinar. We'll send an email out with a link to the recording. And for those people that have asked questions, we'll reach out separately as well. We do have a number of new Apache Ignite webinars on our website. I posted one link in the chat box. Check those out. And I think that brings us to the end of the presentation. Thanks, Dennis and Igor. That was great. Thanks, everyone. Have a good day.
Thanks, everybody. Enjoy the rest of your day. Bye-bye.
Thank you.